We'll look at the MySQL Workbench interface in more detail, as it can help us manage our database better. The symbol located before the name cells indicates us that the object in question is a database. You've seen it before, haven't you? It stands for a database. Moreover, by pressing this miniature triangle, we see how this database can be broken down into 4 components: tables, views, stored procedures, and functions. Since we have not created any of these for the moment, nothing will happen if you click any of the respective names. Don't worry, we will learn more about these concepts and explore their functionalities later on in the course. It is important to be familiar with this little symbol that appears when you hover above the name of the database. It is a feature of the MySQL Workbench you will love when you fill in your database with data. Once you press it, a new tab containing information about the database will open in the right part of the screen. Although all these fields are currently empty, when we fill our database with information, we will be able to inspect its tables, columns, indexes, triggers, views, stored procedures, functions, and grants in a great level of detail. I assure you that we will leave none of these terms unexplained as we move further on in the course. By the end of it, you will understand what each of these components is used for. Great! Alright, we just saw how to obtain information about the cells database and some of its components. However, we don't know how to tell the computer that cells is going to be the database we want to apply the SQL code and operations to. After having created the database, you must type use cells semicolon in the SQL query editor field. By running this line, you will select the existing cells database and you will be ready to apply various SQL commands and data manipulation tasks on it. The latter will be the focus of our next section. For the moment, please concentrate on our next video, where we will introduce you to the most frequently used types of data in SQL. Thank you for watching. Great column. We have already set up our database. Logically, the next thing to create is its tables that, at a later stage, will be filled with data. While doing this, though, we must always specify the type of data that will be inserted in each column of the table. Therefore, in the next lessons, we will introduce you to the various data types available in SQL. Different data types represent different types of information that can be contained in a specific column. There are a few measures that characterize a data type. First, let's say you would like to store the surname of a person in one of the columns of a table. Therefore, to fill in the column with data, you will need letters only. The relevant text format is called string. For instance, James is a string. Length is a measure used to indicate how many symbols a certain string has. For example, the string James has a length of 5 symbols. Jackson, on the other hand, is a string that has a length of 7 symbols. Okay. Digits, symbols, or blank spaces can also be used in the string format. It is very important to note one thing, though. No mathematical operations will be executable within a string. They will only convey text information. Think of addresses. Hugh Street 45 is a string, and you cannot use 45 for addition or multiplication, for instance. Another characteristic you need to understand is size. It indicates the memory space used by a data type and is measured in bytes. You can think of a byte as the approximate space one symbol will require from your memory. So James has a length of 5 symbols and a size of 5 bytes. Finally, consider storage as the physical space in the computer drive's memory, where the data is being saved or stored. Hence, quite often, you could hear phrases like, "This data value occupies 50 bytes storage space," or "This variable takes 10 bytes of storage." In our next video, we'll show you why size does matter in SQL. See you there! In the previous lesson, we said the text format in SQL is called string. For instance, James will be treated by Workbench as a variable of the string data type. Please remember that data formats dealing with information of this type are also called alphanumeric data types. So please don't be surprised if you hear this name quite often. There are a few string data types in SQL. They are quite similar, with the main difference being the storage required to save them. One of these string data types is the character type. The keyword you must use is char, pronounced char. It is a string type that demands fixed storage regardless of the length of the value you are assigning to it. An example will better clarify the concept. Let's assume you have set char with 5 in parentheses. The number 5 represents the maximum number of symbols you are allowed to use in writing a value in this format. Therefore, this column, the name James, which consists of 5 symbols, will require storage of 5 bytes. If instead you type Bob, the length will be 3 symbols, but the storage will still be 5 bytes. Now you see why char is referred to as a fixed storage data type, right? Another frequently employed string data type is varchar. Its name derives from variable character. The variable part regards the storage space needed. Unlike char, varchar will respond to a change in the length of the string that has been inserted. Hence, if varchar is with a maximum of 5 symbols and you enter James, 5 bits of storage will be taken. If you type Bob, 3 bytes, not 5, will be required. In other words, in the parentheses, you indicate the maximum storage a varchar can occupy. Such maximum storage could decrease. It is not fixed, as is the case with the char type. A further distinction between the two formats is the maximum size SQL allows for a char and a varchar type. The former cannot be assigned a limit higher than 255 bytes, while the latter can store much longer strings, up to a maximum of 65,535 bytes. You're probably wondering why char exists considering the fact that varchar is a lot more responsive to the data value inserted. Also, varchar would require smaller storage if the value inserted is shorter than the defined maximum size. The reason is strictly technical, and it concerns mainly advanced users. When processing data, char is about 50% faster than varchar. In our course, this contrast in speed will be of no significance, but when professionals must deal with huge amounts of data, such a difference can become important. Let's look at another example that illustrates a practical application of the two data types. Imagine we would like to add company acronyms in our company's table from the sales database. Each of them will be composed of exactly 3 letters. In this situation, char would do a great job, as it would provide a well-organized column that would process the data efficiently. Alternatively, think of a situation in which you have to store people's passwords. You tell them the password can be composed of any kind of symbol, digits, letters, or others, but the symbols cannot be more than 10 characters. Varchar with a maximum of 10 symbols would do a great job, because a 5-symbol pass, for instance, will not occupy storage for a value that is twice as long. Awesome! This is all we are going to say about char and varchar at the moment. There is another alphanumeric data type I would like to introduce to you. Its name is enum, derived from enumerate. It is particularly handy when you know in advance what type of columns you will be working with. For example, if in a certain column you want to insert the gender of a person, you should specify the possible values of M and F. Then, MySQL will show an error if you attempt to insert any value different from M or F. This string data format is not used as frequently as the previous two, but sometimes you will really love the fact that it is there and can be applied readily. Great! These were the most frequently used string data types in MySQL: char, varchar, and enum. Stay tuned for the next lecture, in which we will explore the integer data type. Thank you for watching. As Your intuition is probably telling you text values are not the only ones you may want to insert in a table you are working with. Often, you will need to use a data type that allows you to store numbers. Numbers are stored in so-called numeric data types. We will go through the types that are most notable: integer, fixed point, and floating point data types. In this lesson, we will focus on integers. They are whole numbers with no decimal point. Numbers like 5, 15, minus 200, and 1000, for instance. The integer, or int, allows us to insert integers into tables. There are a few subcategories of data type, and they are provided in the table you see here. For example, the tiny int type occupies merely a byte of memory and can contain values between minus 128 and 127. Hence, tiny int gives you the chance to designate values between minus 128 and plus 127. 256 different values in total. Don't forget the zero. To understand why each subtype has two ways of representation, we must explain the difference between signed and unsigned values. This is more intuitive than you might think. If the encompassed range includes both positive and negative values, the latter, of course, being signed with a minus, we are in the signed form of representation. In other words, in the tiny int case, signed refers to the range between minus 128 and 127, both included. If we allow integers to be only positive, logically, we will need no sign in the representation of the range of 256 values, hence the label unsigned. For tiny int, this regards storing values from 0 to 255, both included. We must mention one last thing regarding this topic. Remember, integer data types are signed by default. Put differently, SQL assumes you would refer to the upper representation of the given type, the one including both positive and negative values in the range. If you want to use a range containing only positive unsigned values, you would have to specify this in your query. We will see a relevant practical example later in the course. Okay, continuing further, the next data type we'll consider is small int. It is related to a storage size of 2 bytes and values belonging to the range of minus 32,768 to plus 32,767, both included. This is the range when small int is signed. If unsigned, the interval will be from 0 to 65,535. This way, you can read the rest of the table and see the ranges associated with medium int, and big int formats. Now, you are probably asking yourself, why not just use big int all the time? It is the largest interval available for integers, so why bother with smaller integer data type formats? The answer comes with the idea of improving efficiency in terms of computer processing speed. If you are sure that in a certain column you won't need an integer smaller than 0 or greater than 100, for instance, when you are registering the scores of a test, tiny int would do the job perfectly, and you would not need more storage space per data point. Thus, depending on the data that will be inserted in a certain column, a smaller integer type may suffice and increase the processing speed. In the next lesson, we will spend more time explaining the difference between fixed and floating point data types. It is a slightly more interesting topic, I promise you that. Thank you for watching. All right, excellent. To understand the difference between the various numeric types of data presented in this section, we must become acquainted with the terms precision and scale. Precision refers to the number of digits in a number. For instance, we say that the number 10.523 has a precision of 5. The other term, scale, refers to the number of digits to the right of the decimal point in a number. Therefore, this same number, 10.523, has a scale of 3. Okay. Often you will see a data type succeeded by a pair of numbers within parentheses. The first one indicates the precision of the number. and the second one its scale. Therefore, a data type of 5 and 3 will be related to such numbers as, for instance, 10.523 and 36.875. Great! The next important distinction to remember is the one between fixed and floating point data types. Fixed point data represent exact values. Decimal is a good example of this type. Decimal 5 and 3 will contain a value with a total of 5 digits, 3 of which will be after the decimal point. Again, 10.523 would fit. Perfect! Here is something interesting. Should you insert only 10.5, SQL will fill up the number with zeros, so 10.5 would automatically become 10.500. However, if you insert a number with a larger precision, such as 10.5236789, SQL will round this number to a value that complies with the indicated structure, 10.524. And you will see a warning. This is just the way SQL behaves. Okay? Good. Furthermore, when only one digit is specified within the parentheses, it will be treated as the precision of the data type. Writing decimal of 7 would be the same as writing decimal of 7 and 0. Hence, a decimal of 7 or a decimal of 7 and 0 will require an integer written with at most 7 digits, right? For example, the number 1, 2, 3, 4, 5, 6, 7 fits the criteria. Perfect! We shouldn't forget to mention that decimal has a synonymous data type. It is called numeric. Please do not confuse it with the entire set of numeric data types. Integer, decimal, numeric, and the floating point ones you will see in a minute. These are all numeric data types, but this is a specific one. Numeric functions in the same way as decimal and is a fixed point data type. This configuration may sound a bit strange, but this is simply how it is, so we'd better get used to it. Okay? Very good. Numeric and decimal are great for representing a currency. For example, the salaries in a company could be represented by a 7-digit number with only 2 digits after the decimal point, indicating dollar cents. This is the perfect moment to abide by the following syntax. Numeric, P, S in parentheses. P stands for precision, the number of digits of any of the values, in our case 7, and S stands for scale, the number of digits after the decimal point. Thus, a salary of $75,000.50 will fit this numeric data type. Awesome! The other important type is the floating point. It is used for approximate values only and aims to balance between range and precision, hence the first part of its name, floating. Unlike the fixed point data type, when one is working with the floating point type for the precision of 5 and scale of 3, the insertion of the same number, 10.5236789, will not give us a warning. Instead, the number will be rounded to a new one with only 3 digits after the decimal point. That is, SQL will store this data as 10.524, which is an approximate value. So, the main difference between the fixed and floating type is in the way the value is represented in the memory of the computer, as either a fixed point type or a floating point type. In addition, the former will provide a warning whenever its structure is not respected, while the latter won't. Lovely! Float and double are floating data types. The difference between the two lies in the capability of storing data within a memory storage limit, and, of course, this distinction is purely technical. Float needs 4 bytes of memory to be stored. In SQL, this is referred to as single precision. As many as 23 digits can be used to represent a value of the float type. Double is a data type that needs twice the number of bytes, 8. It represents double precision values. A data point of the double type consists of a maximum of 53 digits. Great! A programmer always cares about the exact data type. That's why we pay so much attention to them. It is important to learn the advantages of the various numeric formats within SQL. I hope you enjoyed watching this video. See you in our next one. used to represent. In addition to string and numeric data types, SQL allows you to store data that represents a date, time, binary, or list of options, amongst others. In this lesson, we will cover a few noteworthy data types you will frequently see and work with. Quite intuitively, date is used to represent a date in the format year, month, day, using 4, 2, and 2 digits respectively. Time is not part of this representation, hence the range of date is huge. It is between the 1st of January 1000 and the 31st of December 9999. It seems that this data type is eternal, doesn't it? For example, we could store the 20th of July 2018 in the date format, and it would look like this: 2018 07/25. If storing the date in a record does not suffice and we must store time as well, we could use datetime. Next to the date, we could save the time, shown in the following format: hours, minutes, and seconds. We can even have fractional seconds, parting up to microseconds with 6-digit precision. The range of this data type is one like that of date, with the difference being that the hours can go from 0 to 23 hours 59 minutes 59 seconds and 6 times 9 microseconds. An example of data value of this type would be the 25th of July 2018, 9:30 in the morning. Great! These data types refer to date and time precisely. That is, you can think of datetime as representing the date shown on the calendar and the time shown on the clock. The following type, timestamp, is used quite frequently for a well-defined exact point in time. At first sight, this distinction seems vague, I guess, but in a couple of minutes, you will understand what it is about. Primarily, the range of timestamp is much lower, from the 1st of January 1970 to the 19th of January 2038, 3:14 and 7 seconds in the morning, Coordinated Universal Time, UTC for brief. This shorter span immediately tells us that timestamp will not be the preferred option for storing birth dates and times, as date and datetime appear to be the better option. What is the advantage of using it then? Well, timestamp records the moment in time as the number of seconds passed after the 1st of January 1970, 0 o'clock in the morning. So, for instance, the 25th of July 2018 will be equal to more than 48 years, or 8,535,155,200 seconds, to be precise. Wow! What does that trick allow us to do? Professionals would love to discuss storage space and processing speed differences between timestamp and datetime, but I suggest you remember the following. First, representing a moment in time as a number allows you to easily obtain the difference between two timestamp values. So, for instance, if you know that the start time of an event is the 25th of July, 9 o'clock in the morning, and that the end time is the same day, 10:30, and if you have stored both moments in timestamp, you can subtract the first value out of the second value and obtain the duration of the event. 1.5 hours expressed as number of seconds, 5,400. The second advantage stems from the first one. Timestamp is appropriate if you need to handle time zones, something datetime is not capable of doing. For someone in the UK, something might have happened an hour or 3,600 seconds after the 1st of January 1970, while in Paris, the same event would have happened 1 hour later, at 2 in the morning, as there is a 1-hour time difference. However, the latter need not be stored as 2 hours away from the 1st of January. It would still be recorded as 1 hour after the 1st of January 1970, 0 in the morning. And your computer would handle the time zone difference itself. Therefore, please remember that with such string types as char and varchar, as well as with all date and time types, data in SQL must be written within quotes, allowing it to properly process the respective values. Only numeric values are written without quotes. Another useful data type we'll cover in this lesson bears the name blob. It is derived from binary large object, referring to a file of binary data. Data with ones and zeros stored as a single entity in a relational database management system. Put simply, this data type involves saving files in a record, as opposed to saving data values. Typical file formats that fall under the blob category are doc, XLSX, XML, JPEG, media files, and more. To visualize the idea, think of our customers table. Imagine that people were providing photos as well. If we added a blob column to this table, we would be able to store the JPEG files with the photos in it, and refer to these files according to their customer ID, for instance. Awesome! Remember all these string, numeric, and time data types because they are relevant for more than MySQL. Structured in the same or a similar manner, these data types can be found in every existing relational database, as well as in other SQL supporting software like PostgreSQL or Microsoft SQL. In addition, similar types of data are valid when one is working with programming languages like Java, C++, Python, R, and so on. This will do for now. Thank you for watching. All right, excellent. In this lecture, we will take our first steps into creating SQL tables. Aren't you thrilled? We are. Let's study in a bit more detail the rules allowing us to create a table. In SQL, creating a table is much like creating a database, with one substantial difference. To create a database, we must type create database, preferably, if not exists, the name of the database, cells, and then semicolon. When creating a table again, the DDL's create statement is needed to say create table. It must be followed by the table's name, but before the statement terminator, we must open and close parentheses. Within them, we will place the column names belonging to this table. This is the substantial difference I just mentioned. Another compulsory requirement is to add at least one column. Otherwise, SQL will display an error. This makes sense because there is no point in creating a table that does not contain a single column, right? Where would we store the data? Okay, so here's the syntax we must follow when creating a table. Create table, table name, open parentheses, column 1, data type of column 1, constraints on column 1, comma, then the name of column 2, its data type, and the constraints on it, comma, and so on and so forth until you finish the columns that will be contained in this table. At the end, instead of inserting a comma, you must close the parentheses and terminate by placing a semicolon. All right? Fantastic! Let's clarify this concept through an example in our cells database. Let's look at the relational schema and focus on the cells table. We will need to set up 4 fields, right? A purchase number, a date of the purchase, a customer ID, and an item's code. Cool. Let's begin. All right, create table cells and open parentheses. For better organization of the code that follows, I suggest you start every column in a new line. So, column 1's name is purchase_number. It is of the integer type, and it should be different than 0. As we said in the earlier lectures, it will be our primary key. Cool! There's an interesting extra constraint we can add to this field. It is called auto increment. It frees you from having to insert all purchase numbers manually through the insert command at a later stage. It assigns the number 1 to the first record of the table and automatically increments by 1 for every subsequent row. That is, starting from 1, the next records in this field will be 2, 3, 4, and so on until the last nth record. This feature is designed specifically for cases like the one we have here, when we need to use different numbers in every row in order to provide unique data values that can identify the different rows in our table. Great! Now, let's insert a comma and see the next column we need to create. It is date of purchase. it is obligatory to determine the corresponding data type, date. Assuming we have the requirement to register no purchase unless we also register the day on which they were executed, we'll have to constrain this field to be not null as well. Okay. As you can see from the relational schema, the remaining two fields, customer ID and item code, will make the connection with the customers and the items tables, respectively. While customer ID could be null because we may register a cell without really knowing who the purchaser was, item code must be not null because we will surely know what we have sold, right? Customer ID won't contain anything but numbers, therefore, int will do the job okay. Comma, and then item code. Varchar with 10 in parentheses, as we assume it will be impossible to have an item code longer than 10 symbols, not null, close parentheses, a semicolon, and when we press the little lightning button, we will run the code and be able to create a table. When you expand the sales database and then the table subsection on the left part of the workbench, you'll see that a table with the name Cells has appeared. Awesome! We are done here. Please complete the exercises attached to this lesson. Thanks for watching. Hi, and welcome back. Once again, our focus in this lesson will be on working with databases. A few lectures ago, after we created the Cells database, we said that you must execute use cells semicolon to indicate that you want your queries to be applied to this database. And that's all right. But what are queries used for? How can they help us? One of their main features is to manipulate data within a database. As you already know, data is usually subdivided into tables, and each table contains a certain number of fields. Therefore, when you want to implement various operations specifically to just one table or to a column of that table, you must write that in code, which represents writing a query. Whenever you would like to refer to an SQL object in your queries, you must specify the database in which it is applied. An example of an SQL object you already know about is the SQL table. But later in the course, you will see other instances of SQL objects, such as views, stored procedures, and functions. Okay, there are two ways to communicate this to SQL. The first way is to set a default database, just as we did with the Cells database. Doing so means you will be working with SQL objects that belong to this database. For instance, the Customers table, or another SQL object, can be referred to simply by mentioning their name in the query. The second way does not require you to have a default database. The syntax to call a table from a certain database, in other words, to use the information from a specific table, is the following: name of the database object, dot, name of the SQL object. In computing terms, the dot is called dot operator. It signals the existence of a connection between the two object types. As an example, if you would like to operate with the Customers table from the Cells database, you must refer to it in your query by typing cells.customers, and then continuing with the rest of the code. Both alternatives are frequently applied and used. It is very important to know how to refer to an SQL object in your queries. You'll see why a few lessons from now. In the meantime, thank you for watching. Hi, let's make a few additional remarks before concluding this section. We have already introduced the concept of a query. A query is a command you write in SQL with the idea of either retrieving information from the database on which you are working or, alternatively, to insert, update, or delete data from it. It is a representation of a complete logical thought, solving a subtask required to solve your main problem. The proper way to complete a query is to place a semicolon at its end. Remember we said that a semicolon at the end serves as a statement terminator? Therefore, 2 lectures ago, we ran the code that helped us create an SQL table. It is absolutely correct to say we ran the create table query. Great! If you know how to create an object, such as this table, you should be able to delete it too, right? To do this, you will have to take advantage of the DDL's drop statement. Type drop table, the name of the table, and semicolon. More precisely, the code should be drop table cells semicolon. After you execute this query, yes, though short, this line of code forms an entire query on its own. You can go into the Schema section at the bottom left of your screen, click Refresh, and see that the name cells has disappeared from the table subsection. Okay? Perfect! To summarize, we first created the cells table, and then in this lesson, we deleted it. Now your database is back to its previous state. It does not contain the cells table. Don't skip the exercises following this lecture, which solidify the concepts learned. Then, in the next section of the course, we will introduce you to the really important subject of constraints. Thanks for watching. Okay, so far, we've covered a lot of database and SQL theory, and we've seen how a database can be created. In this section, we'll learn how to assign constraints on tables. This is awesome! We're making excellent progress. Our focus in this lesson will be on the primary key constraint. First and foremost, what do we mean by constraints in an SQL context? Constraints are specific rules or limits that we define in our tables. The role of constraints is to outline the existing relationships between different tables in our database. A few lectures ago, we mentioned that not null is a constraint that can be assigned to a given column of a table. As a matter of fact, we've talked about some other constraints as well. Think about the relational schema of the cells database. You probably remember what primary, foreign, and unique keys are about, right? They define the relationships between tables and designate whether it is possible to see duplicate values in the same column. In abstract terms, you know how these keys work. To apply them in practice, you must define them in SQL through the respective constraints. Okay. Let's start by focusing on the primary key constraint. We'll work with the same cells table. Here is the code we had earlier. It allows us to create the 4 fields we have in this table. You cannot always apply the auto-increment extra constraint for a given field. To do that, this field must be a primary key, a unique key, or an index. That's why, in this block of code, we have used one possible way to assign the primary key constraint. We have just typed primary key among the constraints relevant to the purchase number column, and everything worked okay. There is another way to do the same job. In that case, we need not mention the name of the constraint in the purchase number row. To assign a primary key, we will have to continue the list of elements within the parentheses. So, I'll place a comma after the constraint of the last field. Then, we will continue on the next line. Pay attention, as this doesn't mean that what I write next will necessarily be a column name. Primary key is a reserved word that allows me to indicate the primary key of this table. In our case, the code we need is primary key, open parentheses, the name of the column, which will be our primary key, purchase number, close parentheses, and eventually the closing parentheses of the create table statement, together with the semicolon. To verify that this works, run the query. If you think you shouldn't do this now because you already created this table in an earlier lecture, please remember that we dropped it at the end, so it will be a brand new cells table in the database. Therefore, to execute the code, press this button with the lightning symbol, or, if you prefer, hold Ctrl, Shift, and then press Enter. Alright, fine. Now, let's prove that we did our job correctly. In the Schemas section in Workbench, after you expand the Tables section of the Cells database, you'll have a list with the tables created. For the moment, you have only Cells. As you hover above its name, 3 tiny icons will appear to the right. Press I, which stands for Info. Does this new window ring a bell? We can get an information window related to our database, remember? This time, only the tabs are different. Info gives you some general data about the table. For instance, Columns offers more information about the column names and the respective data types. It tells you what clauses you may apply to the data in the columns and indicates whether you have added an extra constraint. For instance, here is the auto increment constraint on the purchase number. Do you see? However, it would be better if you referred to the DDL tab. It is an excerpt of the DDL statement that has been used to create the respective table. So, in a long SQL file, you don't have to go through the entire code to find that particular bit that refers to the creation of the cells table. In the DDL tab, you will always find the information you need. Here, you see purchase number as a primary key. This means we've done our job properly when we added the row indicating the primary key of the cells table. Awesome! Please don't skip the exercises attached to this lesson. We'll ask you to create the rest of the tables in the cells database, assigning several primary keys. Solving the exercise is a necessary step and will ensure that everything proceeds smoothly when we go on with the next video, Foreign Keys. Awesome! We've already added 4 tables to the cells database. This is great, but we can't call cells a relational database yet, can we? What are the relationships between the tables in this database? You know that they're formed through the interaction between primary and foreign keys. We'll learn how to work with the latter in this lecture. So, let's begin. Can you remember the function of a foreign key? It points to a column of another table and thus links the 2 tables. It is a field or collection of fields from one table called the child table. And it refers to a column in another table called the parent table. Usually, the column or the set of columns in the parent table is the primary key of that table. The child table can also be called the referencing table, and the parent table can be called the referenced table. Good. Now, let's demonstrate how this applies to our database. Shall we connect the cells and the customers tables first? Why not? The primary key of customers is customer ID, and the related foreign key in cells bears the same name. Remember, this is not an obligatory requirement. These 2 keys may have 2 completely different names. What's important is that the data types and the information match. It's just common practice to use, if not the same, then similar names for both keys. Okay, great. So, the customers table, the one with the primary key from the relationship, is the parent, or the referenced table, while cells is the child, or the referencing table. Cool! The theory is clear. And how can we establish a relationship between 2 tables in SQL? Remember the following. A foreign key in SQL is defined through a foreign key constraint. This type of constraint verifies that the values in the child and parent tables match. Technically speaking, We could say the foreign key contributes to or maintains the referential integrity within the database. Good. Let's explore the syntax needed for this operation. Consider the sales table once more. We've already defined all the columns and the primary key. Following the same intuition, we must add a comma and continue with the keyword foreign key, indicating within parentheses the name of the column that will be a foreign key. Unlike with the creation of a primary key, we must not stop here. Let's proceed by typing references, and then indicating the name of the table to which this foreign key refers. In our case, it is customers. Finally, in parentheses, specify the column name, which is the primary key within the parent table, customer ID. In practice, if we leave the closing parentheses and the semicolon at the end, the query will run properly. However, there is a subtlety that professionals regularly add to this line of code. It is the phrase on-delete cascade. What does this mean? Let's analyze it step by step. Cascade means you want a certain phenomenon to affect both dependent objects together and at the same time. This phenomenon is designated by the preceding phrase, on-delete. More precisely, the entire constraint on-delete cascade means that if a specific value from the parent table's primary key has been deleted, all the records from the child table referring to this value will be removed as well. The direction is important, so please pay attention. For instance, if we remove a purchase of customer number 4 from the sales table, we will simply have one less purchase registered in this table, and that will not reflect the customers table. However, if we say Catherine Winfield is not our customer anymore, we'll have to delete customer number 4 from the customers table. Using on-delete cascade affects all dependent objects from the child table, which translates into the loss of the data values of the entire record for purchase numbers 5 and 7 from the sales table. Okay? And this makes sense, right? If we lose a customer, why would the child table need to store a reference to his details when such details don't exist? For this reason, as I already mentioned, professionals tend to attach the on-delete cascade phrase to the foreign key command. Awesome! If you watch our next video, you'll see what happens when we run this query. All that's left to do at this point is to run the query, right? Let's check on the outcome. An error. Wow. And why? Let's see. An error message. Table sales already exists. Aha, right. This is the table we created earlier, and we didn't remove it, remember? We can do 3 things. We can drop the table and then run this code. If we choose this approach, we will have to add a drop table cells statement on top of this query. Let's execute this entire selection. Bingo! It all worked fine. Now, imagine we're having the sales table registered again without a foreign key assigned. So, we will drop the sales table once more, and then we will create it with a primary key only. Hence, the second viable and much more frequently used option is to add the foreign key by altering the already existing table. As discussed in the DDL statements lecture, the syntax we'll need is alter table cells. And be careful here, don't place a semicolon at the end, since this is not the end of the alter table statement. Write add foreign key. Open parentheses, type the foreign key of cells, customer ID, close parentheses. references customers, which is the name of the referenced or parent table, and then put its primary key within parentheses. As we already discussed, type onDelete cascade at the end to remove dependent objects together if necessary. After we execute this command, we can check the DDL tab of the cells table to verify that a foreign key constraint has been created. The constraint, not the column, was automatically assigned the name cells IBFK1. So, instead of deleting the entire table and recreating it with a primary key only, we can remove the newly created foreign key constraint in the following way. We can type alter table cells, drop foreign key, cells IBFK1, semicolon. Run this query and check the Cells DDL tab. Once again, to see that, at this moment, there is no foreign key assigned to this table. Great! Although the focus of this course is on learning SQL by coding, see how the Workbench GUI allows you to add this foreign key, but through the interface without writing code. Right-click on the name of the cells table and select Alter Table. A new window will open on the right side, and you will be able to type the name of the foreign key constraint, which, pay attention, need not coincide with the name of the column. This is just an option for naming the constraint, not renaming the column. Then, you could pick the referenced parent table from a list. Here's the moment to designate the column to be a foreign key and the referenced column. Finally, onDelete cascade can be added from this little list on the right side of the screen. Great! As we press the Apply button, which is located over here, we'll add a foreign key to the cells table. To verify that this happened, look for more information about the cells table. If you check the DDL tab, you'll see that Customer ID has been mentioned as a key, more specifically, a foreign key. In addition, if you prefer, there is a Foreign Keys tab, which contains a list of the foreign keys assigned to this table. On the right side, you can see which is the referenced column, Customer ID, as well as the name of the table to which it refers. This is the referenced or parent table customers. Lovely! In the last few lectures, we not only saw the syntax for assigning primary and foreign keys, we also went through the alter technique, which allows us to implement these constraints on tables that already exist. This is very important. Thank you for watching. Okay, let's recall what unique keys are about. They ensure that all values in a column, or a set of columns, are different. Just like primary and foreign keys, unique keys are implemented in SQL through a constraint, the unique constraint. Each data value of a column that has the unique constraint is intended to be unique across an entire column or set of columns. Therefore, if you attempt to insert an already existing duplicate value in the unique column, SQL will display an error. Consider the customers table from the cells database. Earlier in the course, we said that the email address field is unique because it is impossible to have two identical email addresses. The syntax to abide by is analogical to the one we used when assigning primary or foreign key constraints. Therefore, we have to attach the keyword unique key to the query we created earlier, and that's it. By opening the DDL tab of the Customers table, we can verify we have applied the unique key constraint to the email address field. Fantastic! Now, we will drop the table, and then we will recreate it without setting a unique key. OK, done. There's another way to add this constraint. Given that the customer's table has already been created, the unique key constraint can be added through the alter table statement. Therefore, type alter table customers, and then, for better legibility, preferably on a new line, write add unique key and email _ address in parentheses. Finalize it with a semicolon at the end. Now you can run this query. OK. At this point, we can check the DDL tab of the information section of the customer's table. Yes, the unique key constraint is applied. Awesome! Here's the right moment to introduce indexes. We've left the detailed presentation of this topic for much later in the course. The reason we approach it now is because unique keys in MySQL have the same role as indexes. However, remember that the reverse isn't true. Think of an index of a table as an organizational unit that helps retrieve data more easily. This also means that records in a table can be accessed more quickly. Of course, this doesn't come without a cost. It takes more time to update a table because indexes must be updated too. And that's time-consuming. As a result, think of an index as a MySQL tool that can be created in a column, which will be frequently used to retrieve information from a table. Hence, the automatic treatment of a unique key as an index in MySQL. So, if we want to remove a unique key from a table, we must use the following syntax: alter table, table name, drop index, and not drop unique key. Name of the unique key field without parentheses. To apply this syntax to our ongoing exercise, let's drop the unique key constraint implemented to the email address column. Write alter table customers and then drop index. Email _ address. I'd like to remind you once more not to use parentheses here, as this is the relevant syntax for the drop statement. Right. Execute. Now let's check the DDL tab for the customer's table once more. Here we are. No unique key constraint visible. Wonderful. We'll focus a bit more on indexes later in the course. We had to introduce them at this point to explain how unique keys can be removed. That's all for now. Thank you for watching. All right, let's talk about another type of constraint, the default constraint. You will see it in almost all databases you will work with. It helps us assign a particular default value to every row of a column. A value different from the default can be stored in a field where the default constraint has been applied, only if specifically indicated. A good example is the number of complaints column in our customers table. It is reasonable to think every new customer has submitted 0 complaints at the moment of registration, right? Hence, it is logical to set the number 0 as the default value of this field. Theoretically, in a create statement, when creating the customer's table, the default constraint could be easily added at the end of the row referring to the number of complaints field. After specifying the name of the column and its data type, integer, we must indicate the constraint default. What follows must be the default value we want to assign, complying with the data type set. In our case, we must set 0, surrounded by quotes, or even without. For MySQL, in this situation, using single quotes, double quotes, or no quotes will be the same. As an exercise, you can drop the customers table and recreate it by setting the default constraint to the number of complaints filled. This constraint could be added through an alter statement, and that's the model we'll apply. We can start altering the customers table in the well-known way. After that, we should add the change command. Column, then indicate the name of the column to be changed. Repeat its name, unless you want to change the name too. Then, we must specify the data type and write default 0. Finally, remember we developed the good habit of placing a semicolon at the end of every statement? Let's do that here too. Now, we can run this query and done! Let's check if the default values were applied properly. For this task, we must insert a new record, deliberately leaving the number of complaints column with no value. We'll see if a 0 will appear there automatically. It will be sufficient to add a first name, as we declared it cannot be null, a last name, and a gender, for instance. The customer ID increments automatically, so it is supposed to augment by 1. We do not have to add the email field, so we can just skip it. Let's improvise with Peter Figaro, male. As we run the query, this record will be added to the customers table. To prove this, we can make a check by selecting the list of all records in the customers table. Type select *from customers, and you will obtain a full picture of this table. Bingo! 2 was automatically assigned as a customer ID. Had you inserted more than one customer in the table, this number would have been equal to the next auto-increment value. Peter Figaro, male, appears. The email is shown as null, as we indicated no value for this field in this row, and 0 was put in the number of complaints column directly. Amazing! Setting a default value works. Instead of adding an entire record, you could have verified that the default constraint was set correctly by checking the DDL tab. Let's do this. And no surprise, we see default 0 over here. Therefore, it appears the DDL tab can always tell us if we have implemented a constraint properly, right? Finally, don't be shocked by the fact that the default constraint can be dropped as well. Alter the customers table, then change the respective column, which is number of complaints, by dropping default. This time, I will not remind you to add the statement terminator at the end. Check the DDL tab and do we see a default constraint there? No, we don't. This means we have removed it successfully. Perfect! Create, alter, drop. We use them in almost every lecture related to the creation of the cell's database or some of its objects. Therefore, we can be confident in saying the data definition language, or the DDL syntax, is what we'll use predominantly. It's good we covered it earlier in the course, isn't it? Stay tuned for the next lecture, where we will study the not null constraint. See you there. All right, people, let's see what we remember about not null. When we introduced primary and unique keys, we discussed the main difference between the two. In a primary key field, all your values must be unique, and you may not have null values. In a unique key column, all your values must be unique, but it is unnecessary to have data in all records. This means you can have null values. The not null restriction is applied through the not null constraint. It means that when you insert values in the table, you cannot leave the respective field empty. And if you leave it empty, MySQL will signal an error. In our case, the idea is to keep company details in the companies table. We can see the three columns of the table: company ID, company name, and headquarters phone number. What we will do now is add the not null constraint next to the company name column and see how this changes the functionality of this table. Okay, let's deal with the syntax for creating the companies table. The company ID column is the primary key. Each company ID is associated with a company name and a headquarters phone number. It is fine if a phone number is not provided. The information not to be omitted here is company name. Therefore, when creating this table, after the row corresponding to this column, we must specify the data type, which is varchar 255. Then add the not null constraint. By doing this, we ensure there will be no missing data in the company name column. We did not use the maximal length of the varchar data type. Drawing on my professional experience, we don't need the maximal varchar length every time. To improve performance, we could use the shorter length of varchar 255. It would suffice, and that's why we'll use this value here. Excellent! This time, we'll not even go to the DDL tab of the Companies table to check we applied the not null constraint successfully. But it would be a wonderful idea for you to do this as an exercise. Let's drop the not null constraint through the alter table statement. The syntax that will allow us to do that is specific for the not null constraint. This time, we shouldn't combine alter table with alter column, because we won't drop the not null constraint. In MySQL, we must modify the constraint to go back to null. So, the code we need is alter table companies, modify company name, varchar of 255 null. Execute it. And if we check the DDL tab, you'll see that a not null constraint has not been indicated next to the company name field. Otherwise, we could attach the not null constraint through the alter statement. Alter table companies, then change column, column's name, repeat the column's name and data type, and then type not null. So, when you run the query and check our favorite DDL tab, you can see a not null constraint has been added. Bingo! If we try to insert a row with data where we provide no company name information, we should expect an error message from MySQL. Let's see if that's true. I'll insert just a headquarters phone number because company ID will be automatically incremented, and we want to leave company name empty deliberately. We'll improvise with a random phone number, written within parentheses and within single quotes, as it is a string value. SQL gives us an error stating field company name does not have a default value. This means we have neither set a default value for the company name column, nor have we assigned a company name value to this record manually. If you wonder what the error encountered is, you can hover your mouse over the message field corresponding to it. A little box stating the issue will appear, and you will know precisely what went wrong and what needs to be corrected. This is how the not null constraint came into play. MySQL gave us notice we must insert a data value in the company name field. Great! Let's correct our mistake. Now, we will insert a company name too. Let's say it is Company A. When you rerun the query, you won't see an error appear in the lower section of the workbench, and as we select all rows and columns from Companies, we see our new entry is there. Company A with its headquarters phone number. Awesome! In our next video, you will learn something very important about the not null constraint. Thanks for watching.